Chapter 9, Transmission Modes. Part of this chapter we're going to be talking about the taxonomy of transmission modes, more specifically going into parallel versus serial transmission, transmissions, bits and bytes, timing, asynchronous, synchronous transmissions, RS-234/COM ports. We're going to go ahead and end with our duplexing and our DCE and DTE equipment. The DCE and DTE equipment is very important for serial connections. So again, we're continuing on with the lecture on data transmission terminology. We're going to talk about the advantages and disadvantages of parallel and serial, and go over synchronous versus asynchronous. So what does it mean by transmission modes? A transmission modes is the manner in which data is sent over the underlying media. This happens in one of two ways: serial or parallel. Serial is one bit is sent at a time, i.e. what ends up happening is it does one task at a time, and it doesn't move on to the next task until that first task is fully complete. Serial can be broken down into synchronous versus asynchronous. Parallel is the next transmission mode, and that's where multiple bits are sent over the same time. So a graphical representation of that would be this: parallel versus serial. Serial, again, is one task at a time. The subcategories for serial or asynchronous or synchronous. So when we start talking about transmission, it really is important to find out what are we transmitting. If we're talking about hard drive technology, our serial hard drive technology, our SATA, serial ATA, is actually a faster technology for sending data than it is via parallel, our PATA. I know this is more about our layer 1, but that's always kind of a good reference. So again, our parallel transmission does allow for multiple data sets to be sent over a separate media at the same time. So how this works is we have multiple pathways between the sender and receiver, and it allows multiple bits from different areas to be sent over. This is parallel. However, our diagram did omit two very important areas. All parallel wires that carry data. A parallel interface usually contains other wires that allow the senders to receive and to coordinate, i.e. they are allowed to send and receive simultaneously. This type of installation does allow for better troubleshooting. Also, our parallel mode of transportation has two main advantages. In this type of transmission, it's higher speed, and it has to match underlying hardware. Again, the underlying hardware has to be able to send and receive data in parallel. As opposed to serial transmission, one bit at a time. Though the nice thing with this is it can go longer distance, it costs a little bit less, and it only needs one physical connection. A big part of this is it sends one bit at a time, and thus the logic of it can focus all of its resources on sending that one bit. Here's our graphical representation. Again, it shares a single media. It can share two. That way it has one sending media and one receiving media. The data does need to be able to transmit it between serial and parallel, serial, back and forth. Normally our chips that do that are our universal asynchronous receivers and transmitters, our UARTs, and then there are our USARTs, universal synchronous asynchronous sender receivers. That way we have one that can do just synchronous and one that does asynchronous. So what is the transmission order? Should we be sending data over significant bits or least significant bits? MSB versus LSB? It all kind of depends on the type of technology or system that we're using to send it, but there are differences between the most significant bit and the least significant bit. Either can be used, but both sides have to agree. This is actually one of the odd PowerPoints, because if we're looking at bits, it's little b. If we're talking about bytes, it's big B. And normally when we start talking about bytes, that's dealing with storage, not transmission. When we talk about transmission, we specifically use bits. For example, your network is 100 megabit, 1000 megabit, 1 gigabit. When we talk about storage, we use bytes. We have 100 gigabytes, we have 1000 gigabytes, we have 1 terabyte. Bytes are used for storage. Bits are used for transmission. That's a big thing to get. How do we send the bits? How do we know which ones are the most significant? So if we're talking about Ethernet, we normally separate them in groups of 8 into different octets. Here we have 4 bytes or 4 octets. First byte is our 8 bits. Second one is next 8 bits, 9 through 16, 17 through 24, 25 through 32. This is 4 groups of 8. This is the beginning of basis for our IP addressing. If we're talking about groups of 8, you can call each group, instead of byte 1, byte 2, byte 3, byte 4, octet 1, octet 2, octet 3, octet 4, or the first octet, second octet, third octet, fourth octet. Language is a big thing, so I wanted to point that out. So, how do we deal with timing? How do we make sure everything is going according to a correct time? Asynchronous is any time, while synchronous has a continual time. There is no gap between transmission. And so, synchronous does occur at regular intervals, which means there are fixed gaps, fixed pathways. So these are our 3 most common ones. So again, asynchronous transmission happens at any time. That means you don't have to worry about any type of idle, because for it to be idle, it's kind of arbitrary between transmissions, because the transmission is happening at any time. One of the problems is asynchronous can have problems when there's a lack of coordination between the sender and receiver, because the sender can send at any time, which means the receiver always has to be listening. And then there has to be additional error corrections, just because it doesn't know when it's going to get it. So things like it has to have additional bits and a start bit, just so that the receiver knows where it starts, where it ends. And that's just one of the bad issues with our asynchronous. Versus synchronous, which doesn't suffer from that disadvantage. Next is our RS-232/COM, and that is our standard. We actually don't really use RS-232s as much anymore. That's a traditional serial or COM port, a 9-pin DIMM. So how we actually look at that is Here it is in voltage. When it increases to positive 15, it does the initial start. If it is positive 15, it's representing a 0. If it's a negative 15, it represents a 1. And that's the representation. Next is our synchronous transmission. And again, synchronous means the data is continual, which means that there is no gap. It is always sending. Here's our representation. Here, again, negative 15 is 1, plus 15 is 0, but we're going to be doing groups. It has to know what our groups of 8 bits is, because 8 bits make up 1 byte. So if we're trying to transmit like byte 1, we have to have a start and an end so that the system knows which bits are there. So that brings us into how do we do those groupings? They're done in blocks and or frames. The answer lies within the ability to use framing. Framing actually groups our 8 bits into 1 byte, but it's a specialized code so that it recognizes what portion is the frame. Here we have the start of 1 frame, which are denoted as 3 continual 1s with 8 bits, 3 dots for our completed frame. That way it knows it has the start and an end, and it recognizes how to do that. Last is our Isochronous Transmission, and that is to allow for a steady bit flow. One of the interesting things here is it's a steady rate flow. Things that need less noise, less jitter. Things like VoIP or voice. That way it can guarantee a specific delivery. One of the last major things we talk about is our duplexing. So how do we send? How to receive? Can we do it one time, one way, both ways? Do we have to share media? Normally I want to use like a surface street, for example. Is it one-way traffic flow? If so, that's Simplex. That means it only can flow one way. If traffic can flow one way or the other way, but only once at any given time, it's half-duplex. So that's like when you come to a road and there's construction, there's only one pathway, but the construction workers actually control traffic. That way one set of traffic can go. When they're done, the next set goes back and forth, never allowing both sides to go at once. Only one side is allowed to go at a time. That's our half-duplex. Next is our full-duplex, and that is you can send and receive simultaneously all at the same time. Here's a graphical representation. Again, simplex, one way. Half-duplex, it's send or receive, never both at the same time. Full-duplex is one and the other. It's simultaneously. If you look at copper, you'll notice that there are always, they come in pairs, one for sending, one for receiving. If you look at fiber, same thing, there's one for sending, one for receiving. Half-duplex does have its uses, but I mean, it's kind of limited. We've already talked about our half-duplex, and that is, again, it's one or the other. And there has to be something there so that it can coordinate who's going to send, who's going to receive, and at what time. And how do they know who's going to be sending at what time? Okay, so the last major area for this chapter is our DCE and our DTE. So with our serial connections, we have to denote something that's going to control our time. So our DCE, data communication equipment, and our DTE, data terminal equipment, originally done by AT&T, and is normally done for serial connections. Here, this is what actually is setting our clock rate, our timing. One of the big things here is our DCE controls the clock rate. The DTE is just getting the time from our DCE. So when we program serial connections, the side that's controlling our time is our DCE. For a academic standpoint, we have to make sure that our DCE, again, it's the ownership of our time. It's the portion that controls our timing. It's our time master, if you will. If you take any of the networking / Cisco courses, our DCE is extremely important because, again, that sets our time. So time in what regard? That could be time for our modem, time for our terminals, time for our serial interfaces. It's just dealing specifically with our timing. And that is chapter 6 in a nutshell. Thank you.